Hey, good morning, guys. Assalamu alaikum. Welcome back to Inspired Teams Grade 12 Mathematics. So in today's lesson, we're going to be continuing with calculus. Okay, firstly, apologies for all the delays. It's just, living in South Africa with the water shedding and the load shedding. This creates challenges that you cannot prepare for. Okay, and then the last lesson went on a bit long because I just wanted to finish the section. So that's why we were delayed again. But nevertheless, thank you guys so much for your patience and for joining me. Okay, and we shall start nevertheless, and of course, end slightly late. Okay, so let's have a look at this. We are going to continue with calculus. So we've done tangents, we've done concavity, all the hectic stuff, I think, for the most part, is done. So let's do some of these examples. We're not going to do all, we're just going to probably go through the first one, and then you guys can practice the rest. Okay, but we're going to discuss sketching a cubic function. Okay, when you're given something like this, you're given bullet points, okay, or you're given specifications, okay, or details about the graph, and you are asked to draw or to sketch a graph. So let's read this question. It says, the graph f of x is equal to ax cubed plus bx squared plus cx plus d has 2 turning points. The following information about f is also given. F of 2 is equal to 0. Okay, the x-axis is a tangent to the graph at f is a tangent to the graph of f at x is equal to -1. F prime 1, or the first derivative 1, is equal to 0, and the first derivative half is greater than 0. Without calculating the equation, use this information to draw a sketch graph of f, only indicating the x-coordinates of the x-intercepts and turning points, so only the x-coordinates. Okay, so this is sketching a cubic function when you do not have to formulate the equation, right? You don't have the equation, so you're not forming the graph from the equation. You're not finding the x turning points and intercepts in the traditional way. You're just given certain information, and you're asked to sketch the graph. Okay, so the key here is understanding what each of these things mean. Okay, so let's go to the first one. So here's our little graph here, and we're going to sketch on that. Let's go to the first one. F of 2 is equal to 0. So the first thing we need to note is that in any function, we have f of x being equal to y. So this here is when we have x coordinate and y coordinate. Okay, so for every single coordinate, whatever coordinate is inside the bracket is an x coordinate, and whatever it's equal to is its respective y coordinate. So f of 2 is equal to 0. So the coordinates that form from here are 2 and 0. Okay, so f of x is equal to y. So that's the coordinates x and y. And in this case, f of 2 is equal to 0, which formulate the coordinates 2 and 0. And 2 and 0, this basically represents an x-intercept. So this is what the information is that we're given is. We are given information about an x-intercept. So here they're saying that the x-intercept is 2. Okay, so the following information about this is given. F of 2 is equal to 0. That creates the coordinates 2 and 0, which is telling us that the x-intercept is 0. Okay, let's look at the next piece of information that's given. They tell us the x-axis is a tangent to the graph of f at x is equal to -1. The x-axis is a tangent to the graph, okay, of f at x is equal to -1. Okay, so the x-axis is a tangent to the graph of f. Okay, I was discussing it in functions, but whenever we have, let's just look at a parabola graph. Okay, when we're determining whether the graph is increasing or decreasing, one of the things we could use are tangent lines. Okay, and to see whether we have a positive or negative gradient. So for example, at that specific x coordinate, we can see that the graph is increasing because it has a positive gradient tangent line. So when it comes to the tangent line of the turning point, okay, the tangent line of a turning point always is a always is a horizontal line, and its gradient is 0. Okay, which is actually why, you know, remember we said that gradient is equal to derivative. Gradient is equal to derivative. Okay, and also, how do we get turning point? Right, remember that we always derive it and equate it to 0. So essentially, because gradient is equal to derivative, let's just say derivative gives us gradient, and when we say f of f prime x is equal to 0, we know that this gives us turning point. That tells us that the gradient of the turning point is 0 because derivative gives us gradient. Okay, derivative at the turning point, sorry, gradient at the turning point is 0. Okay, so that's just a little bit of extra information for you to understand that. But the point is that the vertical, the tangent at a turning point is always a horizontal line, or is a horizontal line, okay, with a gradient of 0. So here they're saying that the x-axis is a tangent to the graph of f. Okay, the x-axis meaning a horizontal line. Okay, and if a horizontal line is a tangent to the graph, this means that we are talking about the turning point. So because the x-axis is a tangent to the graph of x, the turning point is on the x-axis. That's essentially what they are saying. The turning point is on the x-axis at x is equal to -1. That's what they are telling us. Okay, so the x-axis is a tangent to the graph of f at x is equal to -1. This means that there is a turning point on the x-axis at x is equal to -1. Okay, so let's look at the next one. F prime 1 is equal to 0. What does this mean? Okay, remember, when we have f prime x is equal to 0, this gives us what? This gives us turning point. When the first derivative equals to 0, that gives us turning point, okay, at that specific x coordinate. So when they give it like this, f prime 1 is equal to 0, they are saying, firstly, this is turning point because first derivative is equal to 0, but turning point at x is equal to 1. That's what they're telling us. So this here is giving us a turning point coordinate, an x coordinate of a turning point. It is giving us an x coordinate of a turning point. Then if we look at this, this is telling us that f of x is greater than 0. This is telling us that, remember, f of x is greater than 0. Now let's go back to our notes and remember, what does f of x being greater than 0 mean for the cubic function? F of x being greater than 0 for the cubic function means that f of x is increasing for those specific coordinates, right? So at a half, it is essentially telling us that, where are we? Sorry, yeah. Okay, f of x being greater than 0, this means that the graph is increasing. Okay, and if they say f prime 1/2 is greater than 0, this means the same thing. The graph is increasing. However, at x is equal to a half. Okay, so the first one tells us that the graph is increasing. The second one just tells us that the graph is increasing at a specific coordinate. So we're given all this information, and this is how we interpret it. And this is the trick of the question, essentially. This is what you need to try and understand, right? All the information that's given, it's not normal. It's not how it's normally given. Like, you don't have the equation, right? You didn't solve for the x-intercept, so you didn't solve for the turning point coordinates, like none of those things. Okay, you were not given an equation, and you are given certain pieces of information. Okay, and you have to draw a graph from that information, and this is how you interpret it. Okay, always remember f of x is equal to y. Okay, and that gives you the coordinates x and y. So when they say f of 2 is equal to 0, okay, by the way, this is the same thing as saying f of x is equal to 0. And f of x is equal to 0 is definitely an x-intercept. And if they say f of 2 is equal to 0, this is an x-intercept at x is equal to 2. Okay, so we understand that that's an x-intercept. Then the x-axis is the tangent to the graph of f. We need to understand that a tangent to the graph, a horizontal line always has a gradient of 0. Not that, sorry. The tangent of a turning point is always a horizontal line. The tangent of a turning point is always a horizontal line. Therefore, if they're saying that the x-axis is a tangent to the graph, an x-axis is a tangent to the graph of f, that means that the turning point is on the x-axis because a horizontal line is a tangent to the graph and the x-axis is a horizontal line. So therefore, because the tangent is a horizontal line, we know that therefore that at that coordinate is a turning point, and therefore that the turning point is on the x-axis at x is equal to -1. Then we look at first derivative of 1 is equal to 0. So first derivative of x gives us turning point. First derivative of 1 is equal to 0 gives us turning point at x is equal to 1. First derivative greater than 0. First derivative greater than 0 means increasing function. First derivative of half greater than 0, that means that it's increasing at a specific x coordinate. So now, utilizing all of this information, we have to draw. So you can first start off by doing your key points, your key coordinates, and that can be let's do turning point. So they say the turning point on the x-axis at x is equal to -1. So at x is equal to -1, I'm going to do turning point. Let's see what's next. Turning point at 1. Okay, wait, let's do the x-intercept, sorry. X-intercept at 2. Okay, x-intercept at 2. Okay, x-intercept says it is red, that's fine. Okay, so this is one x-intercept. And this is another x-intercept. This is the coordinate -1. This is the coordinate 2. Okay, now that we have those x-intercepts in place, so obviously the x-intercepts, we have specific coordinates, like we have definite coordinates because we know that the y-coordinate of the x-intercept is simply 0. So these are the coordinates of the x-intercepts. However, turning points, all the information that we have about turning points, we don't have any y values. So the turning point, all right, excuse me, the turning point, okay, where is the information about the turning point? Yes, we know that one of the turning points is at x is equal to -1. So what you should do for turning points is always draw in a dotted line because we don't know the y coordinates. If you don't know, especially if you don't know the y coordinates, okay, we can draw in a dotted line, and this dotted line is going to represent a turning point. Okay, where is the next turning point? At 1. F of x is equal to 0, a turning point at x is equal to 1. So at x is equal to 1, which is the midpoint between 2. So somewhere here. This is the other turning point. Okay, so we have x coordinates of turning point at -1 and 1, x intercepts at 2 and -1 as well. So What else do we have? We have the fact that the graph, so let me just see, we used the first one, we used the second one, we used the third one, now we need to use the last one. Okay, so the last one tells us that, excuse me, f of x is increasing at the coordinate a half. So here, let's draw in this. Somewhere here, where the coordinate is a half, right, between 0 and 1, at this part, okay, the graph has to be increasing. At that part, the graph has to be increasing. So now what we can do is we can sort of trial and error our shapes. So because we should know that we have two possibilities for this graph. The first one is this, excuse me, and the second one is that, right? There's two possibilities. This is when a is greater than 0. This is when a is less than 0. Okay, so we can try the first one. Let's do this, right? X-intercept, thingy, turning point, intercept. There we go. Okay, so I know that. Okay, so by the way, your turning points don't have to have the correct y value. In this case, you're just going to sketch to your best ability. Okay, that's why in the question they even say only indicating the x coordinates and x intercepts. Excuse me, only the x coordinates we're working with. So how, like, of course, like for example, what I mean is we could have it like that, okay, but it doesn't really matter. You're just drawing to your best approximation what the graph would look like. Okay, so again, I've drawn what? I've drawn x-intercept here, okay, sorry, x-intercept there, x-intercept there. That's fine. Then I have turning point here and turning point there and turning point there. Correct. Okay, so it seems like it's correct. However, it's incorrect because of this last piece of information. It says that f at half, it needs to be increasing. However, if we look at the coordinate half, where this part touches the graph here, we can clearly see that it's decreasing. So what that simply means is that we've chosen the incorrect shape. So instead of starting off with a sad face, we should start off on top with a smiley face. So we start off with a smiley face, then we can go down here, turning point again there. Okay, it's a bit difficult to draw. Smiley face, turning point, x-intercept. There we go. So now we've drawn this, and we can check that at half, it is now increasing, and that is fine. That is perfect, because at half, we want to make sure it's increasing. I've drawn x-intercept there, x-intercept there. I've drawn turning point there, turning point there. And at half, it's increasing. So I followed all the constraint or restrictions that they wanted me to follow. I followed them. Okay, cool. So that's how we draw this type of graph. Okay, so look out. You have to understand what all of this information means. Okay, and it's not too difficult provided you understand the theoretical aspect of your calculus. Okay, and this is a good example covering these. Okay, so you guys should, let me just see, should we do one more? Rather not. You guys can practice it, and yeah, maybe instead, if we have extra time, we can rather work on a calculus question instead. But for now, let us start application of calculus. Okay, so application of calculus, right? The first thing we're going to do is we're going to go through minimum and maximum, rate of change, as well as calculus of motion, right? So these are all three different types of examples that you can get as a question. Okay, so we're going to follow these are going to do the basic examples. Then I'd like to do at least one exam example just to show you how you would go through it in terms of the examination question, because these can get quite tricky, right? They can get quite confusing. I think maybe it's just the way the questions are phrased. But for now, right, let's go through the basics of each. That's most important. Okay, so we're going to go through the basics of each. I'm lost how we got the turning point and the x-axis. How did we get the turning point? Do you mean how did we get the turning point on the x-axis? Okay, so the way we got the turning point on the x-axis is this, with this concept here. The x-axis is a tangent to the graph of f at x is equal to 1. What we need to remember here, okay, is that the tangent to a turning point is a horizontal line. the tangent to a turning point is a horizontal line. Okay, so in order for the x-axis to be a tangent to the graph at a certain coordinate, there has to be a turning point at that same coordinate. Okay, the reason for that is the x-axis is a horizontal line. The x-axis is a horizontal line. So if in order for the x-axis to be a tangent to the graph, so for example, if we look here, right, if we have this parabola graph, okay, and we draw the tangent to the turning point is always a horizontal line, has no gradient, no slope, okay, it's there. And if they say that the x-axis is the tangent to the graph at that point, that means that the horizontal line that is the tangent of that parabola function, in this extra example we're doing, has to be the x-axis. Okay, the tangent line, okay, when the line is, sorry, when the line is a tangent line to a parabola function, okay, I'm drawing a tangent line through the turning point. Remember that the tangent of a turning point is always a horizontal line. And if they're telling you that the x-axis is the tangent to the graph at that point, the x-axis is a horizontal line. And if a horizontal line is a tangent to the graph, that means that that horizontal line cuts the graph, because remember the tangent only cuts the graph at one coordinate. So where it touches the graph has to be a turning point, because if the tangent is a horizontal line, that only happens at turning point. Because let's draw another tangent here. If I had to draw a tangent here, this is not a horizontal line. It touches the graph at maybe that point. Or even the closer we get here, this is not a horizontal line. Maybe it touches the graph at that point. So the only point where the tangent is a horizontal line is at the turning point. And if here they're telling us that the x-axis is a tangent, that means that a horizontal line is a tangent at that point, which basically means that at that point is the turning point. So at x is equal to -1, it's the turning point. Okay, and it's at the x-axis, which means that the x-axis forms that tangent. That means that the turning point is on the x-axis. So if that's what you are asking, I hope that I've clarified why the x-axis is, why the turning point is on the x-axis at this point. Okay, it's because they said that the x-axis is a tangent to the graph. So here you can see this horizontal line forms a tangent to the graph at this point. And the only time a horizontal line forms a tangent to a graph is at the turning point. So that's the reason as to why that is. Okay, thank you for that question. Let's have a look at, let's go back to this. Okay, minima and maxima, or minimum and maximum, are found when the derivative is equal to 0. So we've sort of discussed this concept in functions when we did maximum distance. Okay, we wanted to know what's the maximum distance, what's the maximum vertical distance, let's just say between A and B. Okay, remember that we found the, in that case, what did we find? Okay, okay, we actually didn't do it this way. We did turning point, but I don't know if you guys remember, I mentioned that you could actually derive it and equate it to 0. Deriving and equating to 0 means maximum. That's also, for example, turning point, right? In calculus, right? Remember, we do turning point. How do we find the turning point of a curve? We say we derive it and we equate it to 0. Why? Because isn't the turning point has the maximum and the turning point has the minimum? Okay, so that's why it makes sense, right? Because in order to find the turning point, you derive and equate to 0, because you're finding the maximum and you're finding the minimum, right? The turning points are the maximum and minimum of the graph, or local maximum and local minimum, actually. Okay, so let's have a look at this example. It says that a rectangular box has dimensions x, 2x, and 60 minus 2x centimeters. Questions: determine an expression for the volume of the box in terms of x. Determine the dimensions of the box that would give maximum volume. What is the maximum volume? Okay, so to find maximum or minimum, we can follow these few steps. Set up an equation with the given information. Write a suitable formula for whatever we maximize or minimize, and substitute first equation into the second equation, derive equation, and equate to 0. So let's answer the questions one by one, and we'll go back to see how did we answer these. Okay, so firstly, determine an expression for the volume of the box in terms of x. So remember the formula for volume is length times breadth times height. This is just a simple rectangular prism. So let's take the length of this prism, okay, which is 60 minus 2x. Okay. And multiplied by the breadth, which is 2x. And by the height, which is actually x. 60 minus 2x times 2x times x. Okay, so here we can simply distribute. Let's change the order so it's a bit easier. Let's do that. We can change the order of multiplication, it doesn't affect it. So that when I distribute this into this, okay, I get 2x squared, open bracket, 60 minus 2x. Now I need to distribute this guy. 2x squared goes to the 60, and it goes to the 2x. Okay, so yeah, I'm going to get 120 x squared minus 4x squared. Is that correct? No, sorry, 4x cubed. And I think that's correct now. Okay, so I found an expression for the volume of this rectangular prism by multiplying the length, the breadth, and the height. Okay, so I've answered question 1. Determine an expression for the volume of the box in terms of x. X times 2x times 60 minus 2x. Okay, that's given me 120x squared minus 4x cubed centimeters cubed. That's, remember, centimeters cubed, because that's volume. Okay, and then here they informed us that it was given in centimeters. 1 second, there we go, in centimeters. Okay. So determine an expression for the volume. So when they say expression in terms of x, this is important. They say an expression of the volume of the box in terms of x. They don't mean they want the answer, like they want an actual value, or the volume is 50. No, you just need to express it in terms of x. So your question, your answer can have unknowns of x. Okay, so this is your first answer, 120x squared minus 4x cubed centimeters cubed. Okay, let's look at the second one. Determine the dimensions of the box that would give maximum volume. That would give maximum volume. So we have an expression of the volume. Okay, now we want to know what would give maximum volume. Now, always remember, maximum, whenever we talk maximum of anything, when you say maximum, the word, when you just mention the word maximum, always remember, derive it and equate it to 0. Always derive it and equate it to 0. Whatever your equation is, whatever your expression is, derive it, equate it to 0. So we want maximum volume. So we need to take the expression for volume, derive it, equate it to 0. So that's what we did in the first one. Not what we did in the first one, but we determined the expression in the first one by multiplying the length, breadth, and height. We got an expression. What is this? This is an expression for volume. This is an expression for the volume. Okay. Now, since that's an expression for the volume, if we want maximum volume, okay, maximum volume always includes deriving it and equating it to 0. So if you want maximum volume, you will need to take the expression for volume, derive it, and equate it to 0. So we're going to take this and derive it. Okay, so we'll say that that's volume. So volume prime, okay, that's how we can express it, or the first derivative of volume, or the volume expression, is equal to, so here we can just do regular deriving. 2 times 120, that's 140 x, okay, minus 3 times 4, which is 12, x, 3 minus 1, 2. So this is an expression that represents maximum volume. Okay, actually, firstly, okay, maximum volume, we're going to be deriving it and equating it to 0. So this this is basically the first derivative of the volume expression. And if I want to find maximum, I will take this and equate it to 0. Okay, so these are fairly straightforward examples, right? You want to find maximum, you derive your expression and you equate it to 0. Okay, now we have to solve for x. So what we can do is factorize by taking out a common factor. We have 140 minus 12x is equal to 0. Now you have two brackets, so multiplication of two factors equated to 0. So you can equate each one to 0. So x is equal to 0, or 140 minus 12x is equal to 0. What did they say? Determine the dimensions of the box that would give maximum volume. Okay, so now essentially we are solving for x. So x is equal to 0. That cannot be true. We can't have x as 0 because this length cannot be 0. This distance cannot be 0. Okay, so this is definitely, this is out, right? This is not applicable. However, we can continue here by saying we can take 12x to the other side. 12x is equal to 140, and x is equal to, is there something incorrect? Oh, yes. Sorry. That's supposed to be 240. Thank you guys for that. This is supposed to be 240 because 120 is 200. 120 times 2 is 240. Okay, we derive equate to 0. Equated it to 0. So now we can take out our common factor. And in fact, the common factor I'm going to take out is 12x. Okay, because 12 can go into 140 and it can go into 12, of course. So when we take out the common factor of 12x, we actually left with 20 minus x, which is equal to 0. So 12x is equal to 0, or 20 minus x is equal to 0. X is equal to 0. This is not possible because we cannot have the distance being equal to 0. Or alternatively, x is equal to 20 if I take x over to the other side. So this is definitely the answer. X is equal to 20, and it would be centimeters. Okay, so do you see, when you derive and equate to 0, you actually solve for x first. Like, you haven't solved for the maximum volume, but you solve for the value of x that gives you maximum volume. Okay, so always keep that in mind. That's the first thing that happens. Okay, so in this case, we wanted maximum volume. Okay, we actually didn't. The question wanted to know the dimensions that would give maximum volume. So what should x be in order for this to have the maximum volume? So that's what we calculated, right? We formulated an equation to calculate the volume. We derived it and equated to 0 because that's always how you find maximum. You derive, equate to 0. So we derive this guy, equated it to 0, and we solve for x. And that was, when we solve for x, this gives us the coordinates that would result, or the values of x, or the dimensions, or the value of x that would result in maximum volume. So they say determine the dimensions of the box. So these are the dimensions of the box. Okay, so the dimensions would be first x, which is just 20 centimeters, 2x, which is 40 centimeters, and 60 minus 2x, which is 60 minus 40, which is 20. Is it 20? No, 60 minus 40, which is 20, really? So 20, 40, and then 60 minus 40 is 20. Okay, we had dimensions, but okay. If I'm incorrect, please just let me know. But yeah. Okay, but therefore, these are then the dimensions of the box. Let's look at number 3. Number 3 says, what is the maximum volume? So we've solved for the dimensions that are going to give us maximum volume. Now, in order to solve for the maximum volume, we can simply substitute the dimensions into the dimensions, we can sub it into the volume formula, Because how do you calculate volume? Yeah, we formulated this equation here. We said that this is how you calculate the volume. Then once we solved for the dimensions that give us maximum volume, we can simply substitute it into here. So we can say volume is equal to 120 times 20 squared minus 4 into 20 cubed, because that's the value of x that's going to give us maximum. Alternatively, what you could also do is say volume is equal to length times breadth times height. And the maximum, the dimensions for the maximum volume is 20 times 40 times 20. We can do both and we can see that we'll get the same answer. So here, if I put this into my calculator, which is right here, okay, if I put this into my calculator, I will have 120 times 20 squared minus 4 into 20 cubed. And 20. And here I get a volume of 16,000 centimeters cubed. Let's do 20 times 40 times 20, and I get the exact same answer, 16,000 centimeters cubed. Okay, I just want to reiterate, what is the reason as to why we are not substituting x into this formula? Because this is the first derivative formula. First derivative does not give you gradient. Sorry, first derivative does not give you volume. First derivative does give you gradient. First derivative does not give you volume. The initial equation gives you the volume. So if you have an x value, a dimension that's going to give maximum volume, you can sub it into this equation. Okay, and why do we derive? Because we want maximum volume. That's our first step to solve for maximum volume, or get the dimensions that give maximum volume, by deriving it and equating it to 0. But once we solve for that dimension, we then substitute that back into the original calculation that tells us that calculates volume for us. If you substitute it into here, by the way, you're going to get 0. Okay. So yes, I hope that makes sense. Please, if you guys have any questions, please feel free to ask. But that's essentially minimum and maximum questions using calculus to solve for them, right? Always derive, equate to 0 to find the maximum. Okay, so rate of change. If y is a function of x, then the instantaneous rate of change is dy dx. So this is also the next important thing. The thing we need to understand is that rate of change is derivative. So how do you find the rate of change? You derive it. Okay, so unlike maximum, where maximum is first derivative equal to 0, rate of change is just the first derivative. Okay, if you want to find the instantaneous rate of change, you derive it. Okay, so let's look at this example. The volume of a tank of water at a given time t in minutes is given by, okay, so they've given us a formula to calculate volume. Volume is calculated by saying 10 plus 8 times t minus 2t squared, and it's, of course, it's in meters squared, where the t is time in minutes. So if you want to calculate the volume at any minute, 5 minutes, 2 minutes, 3 minutes, you can substitute that value into this equation and it will give you how much water is in the specific tank. Okay, so that's what this formula is giving. Okay, sorry. Before we continue, I just want to go back to see how we answered this to find maximum minimum. So this is when they don't break it down in the steps that they broke it down in 1, 2, 3. 1, 2, 3, they broke it down. Here is, if you want to just find the maximum minimum, you set up an equation with the given information. That's what we did. Set up an equation for volume. And we solved for it. Okay. Write a suitable formula for whatever to maximize or minimize. That's exactly what we did. That's this. Right. So we set up the equation and then we write the suitable formula. Okay, for what needs to be derived. Substitute first into second equation. What are they saying exactly? And derive the equation equate to 0. Okay, yeah, sorry. So okay, this is for other questions specifically. This is fine. We followed 1, 2, 3. We won't go through that note for now. Okay, we followed 1, 2, 3, and that's how we solve for maximum or minimum. Okay, so let's have a look at this. The volume of a tank of water at a given time, t in minutes, is that. Okay, so we're going to follow those questions in order to answer a rate of change question. Okay, question 1. What is the rate at which volume is changing after 1 minute? So we have, firstly, we have an equation, right? You have to understand what they're saying. We have an equation that gives us the volume. This equation tells us the volume at any time. It tells us the volume at any time, provided we can substitute the minutes into this equation. But now they say, what do they say? What is the rate at which volume is changing after 1 minute? They don't ask what is the volume after 1 minute. They ask what is the rate. Whenever you see the word rate, you need to understand this is first derivative, dy dx. Remember, we went through the notation. This is deriving y in terms of x, right? Or the first derivative of x. Okay, whenever you hear the word rate, you want to derive first. So what is the rate at which volume is changing after 1 minute? Okay, you derive it. So we always have to derive. If we want to solve for rate, we derive. Okay, so just give me 1 second. Okay, so we have a formula that represents volume. They want to know what is the rate at which volume is changing. So again, you want to solve for rate, you derive. So volume is equal to 10 plus 8t, okay, minus 2t squared meters cubed. This is volume. Okay, so now just say you wanted to solve, just say they had a question. What will the volume be at 1 minute? Okay, so this is a different question. They don't want to know the rate at the rate that the volume is changing after 1 minute. They just want to know what will the volume of the tank be at 1 minute. So you just simply take this volume formula and you substitute 1 minute. 10 plus 8 into 1 minus 2 into 1 cubed. And this gives you an answer of 10 plus 8 is 18. 18 minus 2 is 16. So 16 meters cubed, because that's what the formula is in. It's in meters cubed. Okay, so simple. If they ask you what is the volume at 1 minute, you have a formula that tells you what the volume of the water will be after a certain amount in minutes, right? T. So that's a simple question. But they want to know what will the rate be. So how do we calculate the rate? The rate of volume change. The rate of volume change, that can be calculated by deriving the first equation. Deriving the volume formula, so 10 disappears. We're left with 8 minus, is that cubed? Sorry, it's supposed to be, no, it's squared. This is fine, doesn't change the answer, but squared. Okay, 8 minus 40. That's the derived version of the equation. 8 minus 40. Okay, so what is the rate at which the volume is changing after 1 minute? So firstly, we have a formula that represents what? Rate. That's the most important thing. This formula represents the rate at which the volume is changing. Why does it represent the rate at which the volume is changing? Because that's how we calculate rate, by deriving the equation. Okay, now that's just a formula. They want to know what is the rate at which it's changing after 1 minute. So we simply substitute 1 minute into this equation. So first derivative is equal to 8 minus 4 into 1, which is equal to 4. Okay, so what is the rate at which it's, did I do this wrong? No. What is the rate at which it's changing? Okay, so the answer is 4, but what is our units? Our units are always going to be whatever the unit of the equation is, volume, divided by the unit of time that you are using. The unit of time that we are using is minutes. So this is going to be meters cubed per minute. Always the unit divided by the time unit that we're using. Okay, the unit divided by the time unit that we're using, and in this case, it's meters cubed per minute. So that's how we solve it. So the first thing is rate. How do we solve for rate? We derive once. How do we solve for rate? We derive once. Okay, and then at 1 minute, you just substitute it into that equation that you solved for rate. Cool. Let's look at number 2. Okay, so if they wanted volume, you substitute it into the main equation. If they want rate, you derive the main equation. If they want rate at a certain time, derive the equation, substitute that time. Okay, if they want volume at a certain time, use the original formula, substitute that time into the main formula. It will give you the volume at that certain time. Now, let's look at the next one. After how long will the water's volume be a maximum? After how long will the water's volume be a maximum? Okay, so this is using the knowledge of the first part, maximum. What does maximum mean? Maximum means you derive it, dy dx, and you equate it to 0. Okay, it's the same thing as saying first f prime x is equal to 0. That's what maximum, that's what you should always remember. How do you calculate maximum? Derive it and equate it to 0. So that's exactly what we're going to do. They say, after how long will the volume, after how long will the water's volume be maximum? So you're going to take the volume equation, derive it, and equate it to 0. So we already have the first derivative of volume. We calculated it earlier for rate, but now we're using it for maximum. We derive it, but in this case, we equate it to 0. So 8 goes over to the other side. We get 4t is equal to 8. And then we get t is equal to 2. To what? This is we solved for t because they say after how long will water's volume be a maximum? Water's volume will be a maximum. We derived it equated to 0 after 2 minutes. Okay, so we derived it equated to 0. Why did we do that specifically? Because they said maximum. Okay, when will the tank be empty? Okay, when will the tank be empty? That's simple, because in order for the tank to be empty, the volume needs to be 0. So for that one specifically, we just take the volume equation, which is 10 plus 8t, okay, minus 2t squared, and we equate it to 0. Okay, because in order for the tank to be empty, volume needs to be 0. So we equate this to 0, and we can actually, let's just rearrange it. We can divide everything by 2, or negative 2 even. We have t squared minus 4t minus 5 is equal to 0. Okay, so let me just not confuse. Let's just, I rearranged it. Negative 2t plus 8t plus 10 is equal to 0. And then I divided everything by negative 2, including 0, right? It's an equation, so I'm just simplifying it. Since it's an equation, I can divide everything by negative 2 and then ignore it. I divide everything by negative 2, and you get t squared minus 4t minus 5, and you can factorize this to solve for the time to which the volume will be 0. Okay, here you get t minus plus minus 5 plus 1. Okay, so t is equal to positive 5, or t is equal to negative 1. Time can never be negative, so this is not a correct answer. That's an error. So however, so time can be 5 minutes. So therefore, the time at which it will be depleted is in 5 minutes. When will the volume be 0? In 5 minutes. Why? This is simple. We took the volume equation and equated it to 0 because they wanted to know when will the tank be empty. The tank is empty when there's no volume of water. So we take the original volume equation, equate it to 0. One more question I'd like to add. Okay, let's do it. Let's add it after the next one. Okay, we can actually maybe just do it in that example. Let's see. Okay, so that's rate of change. Okay, so we discussed rate, we discussed maximum. Okay, we did incorporate this and that. Okay, so rate, you derive it, maximum, you derive it as well. Okay, but no, sorry, rate you derive, but maximum you derive and equate to 0. Okay, so just keep that in mind. Here we discuss maximum, you derive equate to 0, rate you just derive, and it gives you an equation to calculate the rate. Okay, let's look at this calculus of motion. Okay, so we're going to discuss motion. We have displacement, velocity, and acceleration. We have displacement, velocity, and acceleration. So firstly, to go from displacement to velocity, we derive. To go from velocity to acceleration, we derive as well. And it's seen here, right? Acceleration is dy dx, right? It's the derivative of the initial one. So here we have meters per second square. Where is it? Okay, let's just write it here, I guess. To go from here to here, you derive. So we can say derive displacement, which is s, okay, in terms of time. If you derive displacement in terms of time, you get velocity. Then if you derive velocity in terms of, in terms of time, you get acceleration. Okay, if you derive displacement in terms of time, you get velocity. If you derive velocity in terms of time, you get acceleration. Okay, and then basically, let's just do it in terms of f of x. To get from displacement to velocity, you derive once. To get from velocity to acceleration, you derive once. Okay. To get from displacement to acceleration, you derive twice, because there's two derivatives between the two of them. So acceleration is the second derivative of displacement. Okay, so that's the key thing that we need to understand here for calculus of motion, that velocity is the derivative of displacement, acceleration is the derivative of velocity. Okay, and acceleration is the second derivative of displacement. There we go. Okay, so just always keep that in mind. Example, the displacement of a projectile is given by s is equal to 5t squared minus 20t with s in meters and t in seconds. So the displacement, we have a formula for displacement. Again, the key thing, understanding what equation is given. What are we working with? In this case, we're working with displacement. So this formula, if we substitute any time inside here in seconds, because that's what they tell us, it's in seconds, right? We substitute anything here in seconds would give us the displacement of a projectile, of this object. Okay, that's what this equation gives us. Now, let's have a look at the question. What is the time when the displacement is at a maximum? Oh, maximum. What do you do when you see maximum? Maximum, you derive and you equate to 0. That's maximum. Always remember that. So what is the time when the displacement is maximum? So what are you going to derive? You're going to derive when they ask what is going to be the maximum. In this case, it's displacement. So we look at the equation for displacement, derive it and equate it to 0. So question number 1, we have displacement represented by 5t squared minus 20t. And now we're trying to find maximum displacement, maximum s. Okay, maximum displacement is, how do we find that? We first have to find the derivative of displacement, which is going to be 10t minus 20, and we equate it to 0, because that's how we derive and equate to 0. Okay, that's how we find maximum. Derive, equate to 0. So we've derived it, we equate to 0, and we solve for that t. That's going to give us the time when it's maximum. Okay, so 10t is equal to 20. And t is equal to 2. This is 2 seconds because they told us that the unit is seconds. Okay, so 2 seconds. At what time is it maximum? At 2 seconds. At what time? What is the time when the displacement is at maximum? You can say 2s or 2 seconds. Okay, let's look at the next one. What is the velocity of the projectile after 5 seconds? Okay, velocity. What is velocity? Velocity is first derivative. Not first derivative equated to 0, that's maximum displacement. Velocity is simply first derivative. Okay, we know this. To go from displacement to velocity, we derive. To go from velocity to acceleration, we also derive. To go from displacement to acceleration, we derive twice. Okay, so how do we go from displacement to velocity? We derive. So number 2 is answered how? Number 2 is answered by finding S1, which we already know. S1 is equal to, remember, the derivative of displacement, okay, which is also equal to ds dt, okay, deriving the S, by the way, is the notation for displacement. Okay, you could also use delta x. Okay, deriving displacement in terms of time gives you obviously S prime. S prime is just the easier way to represent it. Okay, which is essentially velocity. Deriving displacement gives you velocity. So the equation for velocity is 10t minus 20. The equation for velocity is 10t minus 20. How did we get that? By deriving the equation of the displacement. Then what did they say? What is the velocity of the projectile after 5 seconds? So this is just an equation that represents the velocity. So we can find the velocity at 5 seconds, and that would be equal to 10 into 5 minus 20, and that's going to be 30. What's our units for velocity? So it's simple. We just have to see what's our units for distance, meters, and what's our units for time, seconds. So remember, like this here, deriving S in terms of t is like having meters, the displacement, over time in seconds. So it's meters per second to the -1. This is the answer. This is the velocity at 5 seconds. It's 30 meters per second. Okay, so let's look at the next one. What is the acceleration of the projectile? The acceleration of the projectile is, remember, keyword here, acceleration. If we have displacement, acceleration is the second derivative. Okay, so let's solve number 3. Now, remember, this is deriving velocity in terms of time, which is equal to velocity prime, which is also equal to the second derivative of displacement, which is also equal to acceleration. Okay, so let's derive velocity, which is equal to acceleration. And if you excuse me, sorry, I tried to mute. Okay, if you derive the acceleration one, okay, let's write out what is velocity is equal to 10t minus 20, and the derivative of velocity would just be 10. The derivative of the velocity would be 10. Okay, and remember, derivative of velocity is equal to acceleration, and it's 10. What's our unit? In this case, we're working with meters, we're working with seconds. Okay, we're deriving velocity in terms of time. The unit for velocity is meters over second over seconds. This results in meters over second squared, which results in meters per second to the -2. So this is meters per second to the -2. And that is the acceleration. In this case, you derived it, right? There's no changing acceleration. It's a constant acceleration. That's why we get a constant answer. So the derivative of the velocity is the acceleration, and that gives us 10, and that's how we get the units. Okay, just the one thing I want to discuss here quickly. What is, if they asked, what is the maximum rate? Okay, we'll probably have one more lesson on calculus where we'll discuss a question, but I just want to discuss this for now. So when they say maximum rate, the first thing is you need to see, okay, maximum, okay, In order to find the maximum, I need to derive it and equate it to 0. But then I also see another keyword, and that's rate. So whenever I see rate, I know that I need to derive it. Okay, so when you have the two combined, okay, what you need to simply do is you need to derive it twice, because here you need to derive and here you need to derive. So you need to find maximum rate is always going to be the second derivative, and you have to equate it to 0 because that's how you find maximum. Okay, so rate maximum derive equate to 0, rate derive it. Okay, maximum rate derive it twice and equate it to 0. Okay, so let's keep that in mind if you're doing any practice questions, but yeah. Okay, let me just have a look quickly before we leave. Okay, we are finished for term 2's work because calculus is term 2. So ideally, we wouldn't like to have another lesson on calculus because we need to start finance. Okay, let's see. I will decide whether next week will be calculus or not, whether we do a question, and then I'll let you know. But yeah, the basics of calculus covered. And then, like I said, either we start finance next week or we continue with calculus. Maybe I'll put out a poll in the group and see what you guys think. Okay, so anything else? Yeah, okay. If there's any questions, I'll be here for the next like 5 minutes to answer any questions. But for now, that brings us to the end of calculus, possibly. Okay. I was supposed to say something, but I totally forgot, I guess. Okay, cool. Yeah, so just keep that in mind, this important displacement velocity acceleration thing. Okay. Okay, cool. For those of you who are free, who need to leave, feel free to leave. But if you want to stay for the questions, or if you have any questions, please, you can ask them now. If anything is confusing you, you can ask them now. But if you need to leave, then thank you guys so much for joining. I will see you guys next week then. Okay, it doesn't appear that anyone has any questions, so let us end the lesson there. Thank you guys so much for joining. I know that most of you guys are going to be starting on Monday, so all the best for school, and I will see you guys next week. Jazakallah khair. Thank you. Assalamu alaikum.